Okay, I'm going to try and smash out a second video this morning. Let's go. So, physical and chemical changes. Primarily what we're interested in here, or what I want you to start thinking about with physical and chemical changes, is that every single time a reaction takes place, there has to be some sort of energy involved, right? It takes work if we want to do stuff. Okay, so what we're going to look at today, we're going to look at different phase changes, and so how energy is involved in changing between different states of matter. We're going to look at different types of chemical reactions, and we're going to go back ahead and we're going to balance some chemical equations, because what we've actually got coming up is really heavily reliant on understanding molar ratios. So that's why we're going to sort of refresh this balancing chemical equation stuff again. Okay, so what I want to have a look at, oops, there we go. This is being a bit slowed. All right, so first of all, let's review the different states of matter. So in chemistry, primarily we're interested in three different states of matter. So we've got solids, liquids, and gases. Now, each of these have pretty distinct properties. So as chemists, we want to know what's going on the molecular level so we can understand why it has the properties that it does. So if we have a look at a solid compound, the particles in the solid compound, they're very densely packed together, right? They're also not really moving that much. They don't really have a high amount of energy. All the energy is sort of stored within the bonds. Then what we're going to do, if we add energy to that, right? So we're adding energy to the particles start to bounce around a little bit more and they start to spread out a little bit more, right? And so once they start to spread out a little more, that's where we get liquid. Now, what happens to the properties? Well, we start off with something that's very, very rigid, very compressed, very dense. And then as we add energy and as the particles begin to get a little bit more free flowing, then we start to see that the volume becomes, the shape becomes a little bit more free flowing as well. Now, the volume doesn't actually change, right? The particles, they're effectively still holding hands. It's like, imagine if you're a solid, it's like a whole bunch of really boring people holding hands standing in a room. And then liquid would be like the party version of that. So everyone's moving around a little bit more, but everyone's still holding hands. Now, if we add more energy to that again, eventually these guys will drop hands, right? So they'll eventually lose contact with all of their other little particle buddies. They'll be really, really high energy. They'll be bouncing around. They'll be wanting to move every single place that they can. So I hope that we can start to see or appreciate why energy changes are so important in physical and chemical reactions. So we've got a diagram here. This is the phase changes diagram, and I've just put in some information here. So I just want to quickly go through this. So first key point, movement between states requires energy changes. And I've kind of outlined why that is, right? Because a gas is highly energetic, whereas a solid is not as energetic. And so therefore, if I want to move between states, I'm either going to have to gain or release energy so that I can move into that new state. So what I've done, I've just put some little stars on here. So this is an aside, right? We're going to talk a little bit more detail about exothermic and endothermic reactions later on. But just so that you guys know, an exothermic reaction happens when energy is released, right? So we start off with something very high energy like a gas, and then it releases some of that energy. It cools down, because remember, heat is just another form of energy. So it begins to cool down, and then it forms a liquid. And then if we continue to cool it down, so in other words, we continue to release that energy from that system, then it will freeze, okay? So this is called an exothermic reaction going this way because energy is being released to the environment. Now with this one here, right, with all these red little stars that I have, these reactions are endothermic because I have to add energy to get them to move to the state that I want them to. Because we start off with a really low energy system as a solid. We have to add energy to get it into the liquid state. We have to add energy again to get it into the gaseous state. So it's an endothermic process when we're moving from a solid to a gas. So this is last little point here. Energy can be heat, and heat, we just call that thermal radiation. That's like the technical fancy name. Okay, so here's just an example of how we would use this in a chemical reaction. When I was at school, my chemistry teacher, like every time we were writing an assignment, she always used to say, you've got to put the science in. You need to put the science in. And I'm like, what the hell is this woman talking about? What she meant was, when you are writing a chemical report, you need to put in chemical equations. You need to put in formulas related to chemistry, okay? So when you guys come to do your assessment, this is the kind of stuff that I'm going to be looking for. I'm going to be looking for these chemical reactions in your assessments. So this is just a simple example to show you how energy can be involved as part of a reaction. So it can be as part of the reactants, or it can be as part of the products. So this is just showing what's going on for vaporization. So with vaporization, we start off with a liquid. We add energy to it because it's an endothermic reaction. And because I know that energy is being added here, that means that it's adding energy to this particular system. And once I've added energy to that system, it gains enough energy to turn into a gas. Okay, so that's all that equation is stating. This is the same thing, it's just in reverse. So obviously I've reversed the reaction. So we're now going back from a gas to a liquid, we're condensating. And so energy is being released on this other side as a product. So that's the other sort of key tip for figuring out whether something is exo or endothermic. Because I've had to add energy here, this means that this is an endothermic reaction. Because energy is being released here as a product, I know that's an exothermic reaction. All right, so chemical changes. So we've spoken before about how when anything reacts, we have this breaking and this reforming of these bonds, and it takes energy to break bonds. But once we reform those bonds, then energy becomes released again, and that's released in the form of heat or light. So for example, if I was burning a piece of wood, the reaction is the carbon in the wood is burning with oxygen to form charcoal or coal or carbon dioxide or carbon monoxide or whatever product of carbon. Okay. And then, so we see that energy released in the form of a flame, and because we can feel that, the heat from that flame, and we can also see the light from that flame. Okay. So there's always energy involved in these processes. So different types of reaction sort of have different levels of energy that's associated with them. I just quickly want to jump through the different kinds of reactions. Now, solubility is not technically a reaction. It's technically a physical process, but these are all different kinds of reactions. So single, double displacement, combustion reactions, combination reactions, decomposition reactions, and very simple redox reactions we're going to quickly go through. All right, so solubility. So we've spoken before, we know that some compounds, for example, like sodium chloride, if I was to come along with a water molecule, because water is polar, right? So because oxygen, he's greedy for electrons, so he's pulling all those electrons towards him in the molecule. That means that the hydrogens become electron deficient or ever so slightly. And so they have these partial charges. And for some compounds, these partial charges are attractive enough, right? So this sodium, we know if we broke that up into its ions, we know that this sodium is slightly positively charged, so it tends to be attracted to that oxygen, while the chlorine tends to be attracted to the hydrogen. And so we can actually split this ionic compound up. But sometimes we have compounds that don't have that option, right? So barium sulfate is an ionic compound, but this water molecule, the partial charge here is just not strong enough to break the bond between these two. Imagine this as like Jessica and Mick from maths last year, right? Jessica, she ain't strong enough to hold on to Mick. That's all it is. And this one would be like Martha and Michael, right? They're a strong couple. They're still together. They love each other. Nothing's going to break them apart. Okay? So this is just a whole set of rules here that sort of outline when things are soluble and when things aren't soluble. So really all you're going to do is you're going to use this information to help you figure out whether something is going to be a solid, okay, or whether something is going to be still dissolved in solution, so an aqueous solution. We don't really need to run through that too much because I'll have to keep referring back to these rules to determine whether or not something is or is not soluble in water. But if you want to figure it out, just jump back. These rules are available in your textbook. I can't remember the page off the top of my head, but it's also a whole bunch of stuff online which have the solubility rules. All right, so let's quickly jump through these different kinds of reaction. Excuse me. So single displacement reaction. So very simply, if I've got a compound, and this compound, let's do a color blue because we know that most people aren't going to be blue-green colorblind, hopefully. Oh, if Jacob is watching, this color is the blue one. All right, so let's jump in. So single displacement, effectively what's going to happen is this one here, this is like our hoe Jessica from maths, right? She's going to come in, she's going to split this couple up, and she's going to take the place there, okay? So she's going to take the place of this guy here. And again, I'm just going to use a little arrow to show because we know we do have some colorblind people. So she comes along and she's like, nah, get lost. And she kicks that person out, and she's now taken over as part of this partnership. So a really simple example here would be something like sodium chloride. My phone alarm's going off. 1 second. Sorry about that. All right. So where was I? So sodium chloride. So sodium chloride is something that is soluble in a solution. So if you go back up to those solubility rules, sodium with most compounds, sodium with most anions is going to be soluble. So that's why I've just given him aqueous. Now, copper, when it's just as like a little sheet of metal, is obviously going to be a solid. So that's why I've written a little S here. Now, when these two react, copper is effectively like our hoe, Jessica, right? So copper is effectively coming in, kicking out the sodium and taking its place here. So it's displacing that partner. And so you can see that this guy has just taken over with the chloride. And I still have to balance this equation out. So we know that copper has a charge of 2 plus and chlorine has a charge of 1 minus. So that's why I balanced it using this particular equation. And then I've had to make sure that I've got the appropriate stoichiometric coefficients for the other compounds as well. And so what this means is that sodium, because sodium is now kicked out of this reaction, because effectively what happens is these guys are dissolved in solution. So let's just quickly draw this. If I had sodium chloride would be chilling in solution, and it would be dissolved, and it would have its 2 ions split apart. So you'd have your sodium and your chlorine ions split up. But then you put something like a copper strip in there, and then all of a sudden, because the attraction between chlorine and copper is so strong, all the chlorine gets drawn straight to that copper. And we get this little precipitative effect. So this copper gets eaten away at and eaten away at and eaten away at. And what we start to see is like a little powder on the bottom start to form. And this is all the copper chloride that starts to form as a little powder. So when we start to have this little solid powder that falls onto the bottom of a solution, that's actually called the precipitate. And so a lot of the time we'll see these compounds, you'll mix 2 solutions together, and then because the attraction of the ions is so strong, you'll see this little powder start to precipitate out, this little insoluble salt. And then we're going to be left with the solid sodium left outside. So this solid sodium will still be just like floating and chilling around. It's not really doing anything. It's just being kicked out of its spot. All right, double displacement reaction is pretty similar to the single displacement, except we've swapped both partners. So originally it was Jessica and Mick, and then who was the other one? Tammy and Dan. But effectively all they've done is swap partners. So now Jessica gets with Dan and then Tammy gets with Mick. So that would be a double displacement where both partners swap. And again, this might happen because, for example, lead nitrate is something that is soluble according to our solubility rules. Sodium hydroxide is something that's soluble according to our solubility rules. So what I do, I have this solution in here. I come along with my second solution. And again, it's a solution because everything's dissolved. Let's pick a different color because you can't actually see the green. Let's do little crosses. So I come in with my second solution and I pour those 2 in. And then all of a sudden, all of these free-floating ions go, hold on a minute. This is actually really attracted to the hydroxide. And so because they're so attracted to each other, they start to clump together and they begin to precipitate out of solution. So this is why this becomes a solid. Whereas sodium, like I said, with most sodium compounds, sodium is, something that's pretty soluble. So that's why it tends to remain in solution. Okay, combustion reactions. Basically, something burning in the presence of oxygen, energy released in the form of heat and light. This is one that we're familiar with. Like I said before, you burn a piece of wood and we can see the flame. We know that there's energy changes involved. Combination reactions. This is another one that's pretty straightforward. So 2 or more elements combine to form a new compound. So for example, this is also an example of a combustion reaction, by the way, because hydrogen gas is burning in the presence of oxygen. But it's also a combination reaction because I'm combining hydrogen with oxygen to produce water. And also energy is released. Okay, second last one, decomposition reactions. So this is basically like the reverse of the combination reaction. So combination, we're combining things to produce a new compound. Decomposition reaction, we have a compound and then that breaks down. So a really sad example is with limestone. So limestone actually breaks down in heat, and that's sad because marine compounds are made up of this. All right, I'm running out of time. I'm going to talk about simple redox reactions in the next video. I'll talk to you guys soon. Bye, guys.